So just to be perfectly clear, this is not the Henk de Vries talk. I was told that he canceled, and I offered to fill in with my coreboot presentation last minute, so this will be about coreboot and not about the talk that Henk de Vries was going to give. I'm going to talk to you quickly about who I am. I'm going to talk a bit about coreboot, some history of coreboot, the competition that we're facing, the motivation for coreboot. I'm going to talk about payloads because that's a big important concept in coreboot. We've also developed a couple of auxiliary tools during the time that we've been working on coreboot, and I'll mention those. I have sort of a demo. Unfortunately, I don't have demo hardware with me, but I'm going to do the next best thing and show you guys a video presentation or a clip of a previous presentation where I did have hardware with me. So it's almost like the real thing. I'm going to talk a bit about security, attack, defenses that can be relevant for coreboot. Not right now, sorry, I have to call you back. Hello? Hi there, I'm up on stage at Haag giving a presentation right now, so I have to call you back. Can I do that? Thank you. Bye. Okay, these things happen. Security stuff, attacks, defenses. I'm going to sort of come to a conclusion, and then I have some thanks and links for you guys. Who am I? My name is Peter Studige, you heard that already. I'm a self-employed consultant in southern Sweden. I do software, hardware, security work, everything from microcontrollers to databases and systems design and whatever. And I also have an interest in security and try to help out there whenever I can. I discovered coreboot in 2001 when I was working as a developer for a hardware company. We were working on developing a set-top box for viewing TV over IP. And this was a PC platform. It was a custom mainboard, but it was still a pretty plain standard PC system. So, of course, we needed a BIOS. We needed something to help us get the operating system running. And I discovered coreboot, or Linux BIOS, as it was called back then. And I thought, this is a really cool project. We should use this in our product. Unfortunately, we chose another firmware, but I stayed with the project because I really liked the idea. And I like to think that I stayed mostly silent watching for a couple of years, but apparently there are some people saying that I was pretty active on the mailing list already back in the start. Anyway, in 2006, there was a developer meeting in Hamburg, and that's not really far from southern Sweden, so I decided to drive down and get together with all the other coreboot developers. I had just installed coreboot on a small via EPIA mainboard in my car, and I talked a little bit about my experience from that as a new user in the project or a newcomer. Because I thought there were some usability issues, usability issues even for developers when trying to implement coreboot. It was kind of tricky, so I wanted to work on that a bit. I took a great part in the design of version 3. I talked a lot about how I would like things to work, improving the design of version 2 wherever possible. We started out designing version 3 at this developer meeting in Hamburg. I've also done a lot of work on Flash-ROM, which is one of the utilities that I'm going to talk about in a bit. Likewise, MSR tool, which is a debugging utility. I've hacked a bit on Philo, a bootloader that goes well with coreboot. I've done some K8, some of the K8 things in coreboot. And I try to do user support and marketing of coreboot as well, because that's important too. So some history for coreboot. The project first started in 1999, so this is a 10-year anniversary. This year is a 10-year anniversary. It was called version 1. The repository name was FreeBIOS. It was the first try. It was really, really simple, maybe 5 lines of code. The truth is it turned out not to work so great with just that little code. It needs to do a bit more. It supported roughly 50 boards eventually, and it still runs in some systems that are deployed. About 2001, version 2 came about, and it had a bit more structure, a little bit better structure than the first attempt. Not so much of a hack. It supports some 140 main boards right now. And in 2006, we started coreboot version 3 at the meeting in Hamburg. A lot better structure, I think, not such a bad hack. It doesn't have that many main boards supported, and by now it's actually sort of stopped. Development has stopped there, but we did a lot of nice things in version 3, and we're trying to move them back into version 2. So version 2 remains the popular version and the main, really main repository for the project. But we're moving stuff in from version 3. Most notably, maybe lately, is kconfig. So version 2 previously used a proprietary, well, not closed source, but still our own configuration file format. And turns out that's not really so easy to work with. And for version 3, I really pushed kconfig, the configuration system which is used for the Linux kernel. So that's in version 3, and it's also on its way back into version 2 right now. So I think that's really good. We managed to do design testing on a handful, several embedded x86 mainboards using the Geode-LX CPU from AMD. So what is coreboot? I think you're all brave for being here because the program was changed a little bit last minute and there wasn't a lot of detail, so I'm happy to see you guys here. Coreboot is a BIOS replacement, an open source BIOS replacement for PCs. So an x86 firmware. And looking at the BIOS, what does the BIOS do? It has 2 tasks. The BIOS does hardware initialization. First off, it starts up the system so that software can run on it and can use all parts of the system. Then the BIOS goes on to start the operating system. It loads the master boot record, or it reads the master boot record from hard drive. It might start up a bootloader. Maybe you're using Lilo or Grub. Or it can read the CD-ROM or a USB memory stick. And the BIOS also provided interrupt services. That's a software API for applications running in the system to do basic input-output. That's what the acronym is stand for. In reality, no one is using these interrupt services anymore. All the operating systems nowadays, they have their own drivers for every piece of hardware. So the interrupt services have become pretty much obsolete. Only DOS is really using them, and the very early stages of some bootloaders also use them. So we have hardware in it, and we have the operating system starting. Why do we even look at coreboot? What's the purpose of this? Why are we doing this? There's a number of reasons. First of all, it's open source, and none of the traditional PC firmware vendors have open source products. So that's a big deal. Second of all is sort of related to the open source fact. The people who started working on coreboot back in '99, that was the Los Alamos National Laboratory in the US. They were building a supercomputer cluster with a couple of thousand machines, and they really didn't want the keyboard error, press F1 to continue message on their 4,000 machine cluster. So they did the only natural thing, and they started an open source firmware project. Also, I think another reason why coreboot is really relevant is that we see a number of things coming up now lately, the last few years, in the security research field, where there are issues and risks that I'm going to mention a bit later, with the firmware, and because we don't really know what's going on there, and we don't have a full insight into this execution stage. There's a lot of stuff that can be going on there, and that's not really so nice. So the BIOS doesn't work really now the way it used to. I mentioned these software interrupts. They really worked as an API. So the operating system and applications would call into the BIOS to do simple I/O, like output characters on the screen or to the serial port, or maybe read from the keyboard or whatever. And this was how the system ran, and it's not really different from an operating system, just that, or not different from today, just that today the operating system has all the drivers and the BIOS isn't really involved at all. So this changed when the first laptop came about. The first PC laptop, it had a lid so you could close it, and when the boss closed the laptop lid, he of course wanted it to shut down automatically. So there came APM. That was the first power management technology used in PCs. When you close the lid, the processor would switch into a new execution mode called system management mode, and do a shutdown, a clean shutdown of the system, sort of pause everything that's going on in the system, and then power off, so that you could just close the lid and pack the laptop in your bag. So how many of you guys know about system management mode in here? Okay, maybe 10 out of, say, 80, 90? That's good. It's good. System management mode, as I said, it's a new execution mode introduced in the 386 SL processor. So this is a really old technology, almost 20 years old. When the processor switches into system management mode, it really freezes time. So whatever is happening in the computer is completely stopped, and no changes are allowed. All the state is saved. Once in system management mode, the processor can execute some small functions and really do whatever it wants to, because the normal system is completely stopped. So all state is saved, and a pre-configured system management mode handler is executed. And there was also an electrical signal added to the processor, so a new pin, a new interrupt pin, which is, of course, what was used for signaling that the lid was closed. So when you close the lid, this pin wiggles on the CPU, and the CPU switches, pauses whatever is running in the operating system, switches into system management mode, which will do hibernation, save state to hard drive or to memory, and power off. It's not only this new interrupt signal, though. System management mode can also be invoked by SMI traps. And these SMI traps, they're really a software filter. So you set up a number of rules where accesses to particular RAM locations, so particular addresses in RAM, or particular I/O ports, I/O addresses, will in fact trigger this system management mode. And using this technology, you can quite easily virtualize hardware. Because, for example, the PCI bus runs really completely off of 2 I/O ports, or, well, 8 I/O ports, 8 I/O addresses. And if you hook these I/O addresses to go into system management mode, an operating system trying to scan the PCI bus could, when it reaches a special point, be moved into a system management mode, or the system switches into system management mode, and there's a system management mode handler which replies just as if there was actually a PCI card plugged in. But in fact, it's just a virtual PCI card running in system management mode. AMD Geode, the Geode series, which is what we were using in the set-top box, and also something that's been well supported throughout the history of Linux BIOS and coreboot, because AMD really help us out a lot. The Geode platform, it works like a PC, but it's really a new architecture, and it uses system management mode to virtualize PCI devices like I just described. Also, any PC that you might have that supports USB keyboards and USB storage in the BIOS will be using system management mode, especially for the keyboard emulation. If you have, if you're able to plug a USB keyboard in and still type stuff on that to your bootloader, then you can know that your USB BIOS, or your USB BIOS is running some system management mode handler. The PS2 keyboard is also using I/O ports, so when the bootloader tries to talk to the PS2 keyboard on these I/O ports, in fact it triggers system management mode, which will communicate over USB instead, and then return a result just as if there was really a PS2 keyboard. APM was the start, the first try at some kind of power management, power awareness in PCs. After that came ACPI. So ACPI is the Advanced Configuration and Power Interface Specification, conjured up by friends at Hewlett-Packard, Intel, Microsoft, Phoenix, the major BIOS vendor, and Toshiba. The revision 3 document, which I've had access to, or which I found, is from 2006 and some 600 pages. Among other things, for the configuration part is pretty simple. It specifies tables of what hardware is in the system, how much memory do you have, etc., etc. Nothing really spectacular. For the power part, it specifies a virtual machine which has its own bytecode. And this virtual machine runs in your BIOS. So outside the security controls of your operating system. Is it really outside the operating system? Yeah, at first they implemented it that way, but it turned out to be way too slow. The performance hit was, I've heard the number 5% performance lost because the ACPI virtual machine was implemented all in the BIOS. I'm sorry, I just remembered I forgot to plug my laptop in. There we go. This virtual machine, it moved into the operating system because of this performance hit. It was just unbearable to have 5% gone. And Linux started doing this in 2001. I've seen the number 90,000 lines of code in the Linux kernel to implement the ACPI virtual machine at present. And the good, or the fun, interesting part is that it still operates outside the operating system security model. It's how ACPI was designed to work, how it was designed to run, and it's the only way it really can work. So, yeah. And who is providing this ACPI bytecode? Well, it's in your BIOS, so it comes from the BIOS vendor. Okay, looking around, what's out there in this field? For the PC, there's really two options. There's BIOS. There are a few BIOS vendors left. Really only two big ones. That's Phoenix and that's AMI. They bought everyone else. It started out in 1978 with a tape player I/O abstraction. So there were two brands of tape machines, and there were a couple of different PCs. And in order to talk to the different tape drives, you had to drive them a bit differently. So the BIOS was implemented to abstract the differences. And that was really all it did to bootstrap the system. In 2009, it's an API with well over 100 function calls. A lot of stuff that can be done if you ask the BIOS. Mostly real mode code. I listened to a presentation by one of the commercial BIOS vendors, and they said that, well, our code base, it has 4,300 files in it, all assembler files. But they said it's modular, so it's really easy to work with. I don't know, I would probably prefer a bit fewer files myself. That's the BIOS. It works the way it always has. Then there's the new guy, that's EFI. Originally started by Intel. It's almost an operating system. It has its own network stack. It has support for timers. It's really modular compared to the BIOS, which is just one big lump. It's possible to download a development kit called Core from the web. It's BSD licensed, about 250 megabytes. And compare that with Linux, which is maybe 50 megabytes. EFI is claimed to be open, and in fact, I've heard that the BIOS vendors, they were really scared of EFI when it was first started by Intel, because they thought, oh, okay, now open source firmware, now we're not going to have any market for our products anymore. But in fact, the open part of EFI is really just the foundation, and the BIOS vendors, they're all using that foundation, and they're adding building blocks onto that. So they still have their products. That worked out well for them, but it's not so nice for us because they make all their products closed. Because it's BSD licensed, that's okay to do. But still, I would prefer an open alternative. That's it on the PC, and of course there's coreboot. There are some related projects. Maybe you've heard about Grub and Lilo. I guess many of you are using either of them. They are bootloaders, and they relate to this field, but they run after the firmware is done. So first we have coreboot or BIOS or EFI, and then we move to a bootloader, which is started by the BIOS or the firmware, and the bootloader is responsible for starting up the operating system. There are some other options like Redboot, U-boot, and PMON. And there's also PMON 2000 for the Lungson processor and some MIPS processors, but they're really not so much for x86 architecture. They're more popular. I know U-boot can be made to run on x86, and maybe someone is using it already, but other than that, they're all for smaller systems. Otherwise, they have the same function. They initialize the hardware, and they get the operating system started. So I said coreboot is a BIOS replacement, and we talked a bit about how the BIOS works, how it's split into the hardware init and the operating system start. And coreboot does things differently. I think much better and at least very differently. Coreboot only does the first part, the hardware initialization, and then coreboot is finished. Coreboot doesn't run anymore. After the hardware initialization, there's a separate program which has to take over and do whatever should come next in this system. And we call that program a payload. Coreboot, the payload with coreboot, it can do whatever it wants. It can start an operating system. It can be a utility, some kind of application. There's really no limit to what can be done in the payloads. You're the only software running in the system. You have full control. Many times it is a bootloader because you want to maybe start an operating system. Coreboot and the payload, we put those two together in the coreboot build process, and then the result is flashed into the BIOS flash chip on the main board. So out with the BIOS and enter coreboot and payload. What are all these payloads then? Or what payloads are there? There's a whole bunch of them. Originally, the idea was to use only a Linux kernel as a payload, as the only payload. And that's also the reason for the name initially. The project started out being called Linux BIOS. The idea was to use Linux as the BIOS. Unfortunately, that could only work if the flash chip size on mainboards increased, and while costs have gone down a lot, the sizes haven't really gone up that much. Typical size for a BIOS flash chip today is 0.5 megabyte or maybe 1 megabyte, and that's really not enough to put a Linux kernel in there. With 1 megabyte you can squeeze it in, but it's a lot of work, and many times you can't get everything you want into there. So people wanted to use this anyway, and they come up with other payloads. We have a bunch of bootloaders. There's Philo, which is developed by also coreboot developers. It's a bootloader for starting Linux and multi-boot images off of local storage, so either hard drives or CD-ROMs. There's also a project to get USB. There is already USB support for UHCI, the Intel and VIA host controller interface, but there's also a Summer of Code student working on adding OHCI and EHCI support to that stack. There's Grub 2, and that can be used to start a lot of operating systems in many formats and from many media, so also local storage, of course. There's Etherboot and GPXE. Maybe you've already used one of those for starting an operating system from the network. CBIOS is a very, very nice payload for migration. CBIOS is really a standard BIOS implementation. So if you combine coreboot, which is the hardware initialization, and CBIOS, use CBIOS as the payload, you get an open source BIOS compatible firmware for your PC. And you can start any existing operating systems or any operating systems that the BIOS can start. So it can run BSD and Mac OS and DOS and Windows without problems. There's also an open firmware payload. Some people have mentioned the project name OpenBIOS to me, and that was in fact an open firmware implementation for PCs. So OpenBIOS could be used as a payload with coreboot. And I've also written Linux up here as a bootloader, and maybe that's strange, but again, the original idea was to have Linux in the boot flash in order to utilize all the drivers that are available in the Linux kernel and not have to rewrite them for a bootloader, because we have working drivers for everything in Linux already, so why not try to use them for booting the operating system also? Plus, they're a lot more, they've had a lot more testing and they've been used a lot more, so there are probably less bugs in them as well. The really nice thing is that you can also use a lot more drivers because Linux has drivers for stuff that isn't already in bootloaders. CD-ROM and hard drive and stuff like that, that's the easy part. We've seen a couple of bootloaders mentioned already that implement drivers for that hardware. But if you're using Linux as a bootloader, you can use, for example, Wi-Fi to boot your system, or you can use MirrorNet, or you can use iSCSI, and you don't need anything else. You don't need an option ROM. You can use any simple controller card, any simple network card, and it will run just fine. Also, because space is a bit tight in the boot flash so far, it might be a good idea to have sort of a two-stage startup process. So you have one small Linux kernel running as the bootloader, as the payload, and that kernel can, since 2626, I think, start another kernel. So you have the small one running out of flash, which loads up the iSCSI driver, contacts the iSCSI storage, and there is a full-size kernel with all the stuff enabled that you need to run your system. The boot kernel can then hand over execution to the full-size kernel, and you have a very, very easy and fast way to start up the system. But payloads can be utilities as well. You don't need an operating system all the time, so you can run stuff like memtest86 directly from coreboot to do memory testing and find out if there are some problems. We use that a lot, of course, during development to check that the memory configuration done by coreboot has actually succeeded, is actually correct. There's coreinfo, a small utility that we developed also for inspecting the PCI bus, inspecting NVRAM contents, and really debugging mostly CPU information, and also finding out about the coreboot that was built. Linux is up here again, because if you can put a Linux kernel in the boot flash, you can add, of course, an init RAM FS. And in that init.ramfs, you're free to put whatever utilities you want. So you can say, run secure shell from a remote system into your BIOS, or you could at least have a familiar shell prompt in your firmware environment. Ron Minnick, who is the guy who started coreboot, he jokes about open firmware because when open firmware starts up and there's a problem, it will, of course, stop the boot process, and it gives you a prompt asking for some kind of input. And the prompt says, OK, when in fact the boot has stopped and everything isn't really OK because you want to be in your operating system. And his point there is that if you have a Linux kernel and a small file system, small init.ramfs, in the boot flash, then you're always in your most comfortable environment. You always have access to your shell utilities, your shell, all your shell tools that you can pack into the flash chip. So that's nice. Applications, I mentioned briefly also, we have some fun applications. We've ported a few games to run as coreboot payloads, a Tetris game, Tint. There's also a Grub Invaders, which runs just fine. And Bayou deserves a special mention because I mentioned that there's just one payload, or I mentioned that coreboot starts the payload and there's no way to go back. So there can really be only one payload. But maybe that's not enough. I want both Philo and memtest86, and I want to play Tint sometimes. So what do? I have to use Bayou to first pack these different payloads together, and then Bayou will be the main payload that I use. So it combines multiple payloads into one, and either provides a curses-based, a text-based menu, or it can be scripted to run stuff in sequence automatically. Tint and Bayou and Coreinfo and Philo and probably some payloads I don't know about are all using libpayload, which is a C library that we developed, really small C library. It can be used to very easily compile a simple C program that doesn't use any operating system services to become a payload. So instead of running GCC on your C source code to create the Linux binary, you just run LPGCC, which is the wrapper script that comes with libpayload, and out comes a payload binary instead of this Linux application. Inside libpayload, there's also tiny curses, curses implementation, so that you can build these text-based user interfaces. And the API is compatible with the standard curses API, so you can test stuff running in Linux and then just change the compile command or the build command and have it run as a payload. Some auxiliary tools that we've created during the development of coreboot. There's buildrom. Buildrom is good because there's quite a few things to keep track of in coreboot. There's the coreboot version, there's which mainboard you're using with coreboot, there's the payloads, the payload might need to be configured, coreboot might need to be configured. Buildrom takes care of all of this, and you just use one simple kconfig interface, pick a few things, your mainboard, your flash chip size, which payload you want, and you let it work for a while. Out comes your ROM file, which you can flash into your flash chip. Make elf image is something we used a lot earlier to make a Linux kernel image into a payload. I believe it's no longer necessary with the latest changes in version 2. But it's still up here because we used it a lot, and we still keep it in our repository. NVRAM tool, I mentioned briefly, it's for changing NVRAM settings, the battery-backed couple hundred bytes of memory, which is in your computer. The standard BIOS uses that to save settings as well. And so does coreboot. NVRAM tool uses a sort of a descriptor file, so it can be used to work on standard BIOS settings as well, not only coreboot and payload settings. Super I/O tool, Intel tool, and MSR tool, they're all pretty much debugging utilities for development. But also, short troubleshooting and finding out why a system isn't working. They're really good at decoding all the register values that are in the various chips in PC today. I also want to mention the tool FlashROM, especially. I've done a bit of work on that. Now I'm not so active there anymore. It's a BIOS upgrade tool for running on x86 BSD and Linux and Solaris and Mac OS X. So you're no longer required to reboot onto this FreeDOS floppy disk that you have to create every time you want to upgrade your BIOS. It supports cross-flashing. You can flash one flash chip, one BIOS image on a flash chip on a mainboard, which is different from the mainboard where the flash image is going to run, or the BIOS image is going to run. Standard BIOS flashing tools from the vendors, they usually don't allow this. Supports hundreds of flash chips and lots of chipsets, and the mainboards that are up here, 23 looks like a low number, and that's because it's only the number of mainboards that FlashROM needs to know about. There's also many hundred mainboards which just work, and FlashROM doesn't need special support for them, so FlashROM runs just fine on those as well. Push-pin flash is a fantastic idea that I wish I had come up with. If you have a couple of flash chips and you're moving them around, then it's really nice to take this corkboard pin, heat up the metal a bit, pull the pin out, and glue the plastic knob onto the flash chip. So you get a nice handle for the chip, and you can also color code them so you can remember which is the original BIOS that I should never, ever write over, and which are the development chips that I can use. No, this should work. Just a second. Where are we? Oh. Device or resource missing. There we go. So now there should be sound. An Alex 1C CPU board, that's an AMD Geode-LX CPU. It's a PC system with an AMD CPU, 256 megabytes of RAM. Made by a Swiss company. Pretty nice hardware. Let's see. We have a serial console. So looking at the output here, we have a serial console. And I release reset now. We see coreboot starting up, and it finds the Linux kernel. The Linux kernel is starting now, and we're up. So that's the full boot process, and it's pretty snappy on this mainboard. Yes, it worked. It's always dangerous to do demonstrations on real hardware. Really quickly, some risks that we're facing without open source x86 firmware. We have RAM readout issues. If someone can come in and take control over the machine right after we've done a reset, then they have the possibility to read all of the RAM contents which was in the machine before the reset, and maybe find cryptography keys or other things that we would prefer no one else has access to. It's easy to do TPM emulation or TPM sharing, so you want to play some music on the fruit box over in the corner. You can do that by using the same virtualization tricks that the USB BIOS uses for keyboards. System management rootkits have been popping up at security conferences lately, and it's of course possible to do anything that is, virtualize anything that is using I/O. Remote hard drives, have some fun with fans and make the fans spin at various speeds to create sound. You can play audio that way. User lockout, force someone to play tint if you use coreboot for an attack. And the last, I think, popular thing is to do code injection or modification of the operating system from the firmware. So the firmware runs and changes little bits and pieces inside the operating system so that when the operating system starts up, there's a backdoor and whoever created the BIOS or controls the BIOS can really control the machine even though the operating system is running and only I know the root password. What can we do to defend ourselves using Open86 firmware? We can make sure to clear all memory when we're shutting down. We can detect whenever someone opens the case and do the same there. We can filter the ACPI bytecode, implement ACLs depending on what kind of attachments or devices, peripherals are attached. Virtualization, do encryption on the fly. We can make sure the flash chip is locked down so no one can read or write to it. And in conclusion, there are some good things about coreboot, I think. Really short startup time, as you had a chance to see. It's open source, that's important. GPL for coreboot itself, but it's important to us that the payloads are separate so that they can use a separate license. So coreboot uses GPL and the lib payload is BSD licensed. Auditability, so you can really check what's going on inside your firmware, written in C instead of assembly language. There's one source tree for all the roughly 200 mainboards that we are supporting right now, meaning we have a lot more reusability, chances for reusability, and it's much easier to extend the source code than if you're using an assembly firmware. Challenges, we still need to do more testing to keep the quality increasing instead of decreasing, which might happen at times. We do compile testing of every mainboard at every commit, but we can do even better. We'd like to do even better. We need to polish all the boards in there to a full 100%, but most of the boards aren't really far away, so it's many times mostly a matter of someone stepping up and having the board and wanting to straighten the wrinkles that are still in there. We still have to do some work on a clever ACPI implementation or a clever ACPI infrastructure, I think. Rudolf Marek and Stefan Reinau have already done some great work. And that's kind of where I'm going to look in the future also a bit. So there's a lot of fun stuff going on. Please come see us. I'm here. I'm in the hardware hacking BSD village. And I have to say thanks to Wim van de Putte and Fabienne Serrea of the hardware hacking village and BSD village for setting up a really great environment. Please come, talk to us, check it out. And also thanks to Tim Gemmel for booking me into this slot that opened up in the program. So we have a website, coreboot.org, mailing list. Please join and come talk to us. We're also on IRC, on Freenode, #coreboot. I'm Care Bear. The coreboot.org website is a wiki, so you can add almost anything afterwards, after the domain name that you want, or you can use the search. So that's all I have. Do you have any questions? I know we're running out of time a bit, but maybe there's time for just a few short questions if there are any. There's a question. Yep.
Does the system management mode also stop real-time timers?
I'm sorry, I can't hear you.
Does the system management mode also stop any real-time clocks on the system?
I still can't hear you.
Does the system management mode stop real-time timers?
So the question is, does system management mode stop real-time timers in the operating system? And the answer is yes. System management mode stops everything in the system. So system management mode can definitely have an impact on your system if you are running something that is sensitive to real-time performance. All right, no more questions. So thank you very much for listening to me. And feel free to... feel free to find me later or in the BSD Village if you want to talk more.
Thank you.
No problem.